Well, hello, I'm the amateur logician. I hope you are doing well. Together, we're going to prove that two lines that are parallel have the same slope. I think it's a pretty cool proof we're going to do. We're going to attempt two proofs, actually. And the question of why parallel lines have the same slope on one level is actually very intuitive. As long as they are not the same line, the only way they will never intersect or touch is if they have the same rate of change. If one has a different slope than the other, then one, so to speak, is going to overtake the other one sooner or later. It has a faster rate of change, and so because we're dealing with lines that extend to infinity, sooner or later they will meet, they will cross. Let's say we have the Cartesian coordinate plane, the xy plane. Let's say we have this line, L sub 1, and this line, L sub 2. So any standard textbook would tell us they are parallel if they have the same exact slope. But consider, for example, something like y is equal to x and 2y is equal to 2x. To be sure, those equations look different, but if we graph them, we would get the same exact line. Because, in fact, they are equivalent equations. They look different, but they're equivalent, because obviously the second equation, we can simplify it and just get y is equal to x if we divide the left-hand side and the right-hand side by 2. So in general, if we have y sub 1 equals m sub 1 times x plus b sub 1, and y sub 2 equals m sub 2x plus b sub 2, those two equations produce linear lines. They're parallel if m sub 1 equals m sub 2, but b sub 1 does not equal b sub 2. Or in other words, they have different y-intercepts. So here we might say with line 1, we have b sub 1. Here we have b sub 2. B sub 1 does not equal b sub 2. They have different y-intercepts, but their slope is the same. So m sub 1 equals m sub 2. So let's consider the first proof, which is very Euclidean-like in style. And it's pretty cool because it doesn't have many assumptions. We're going to use these basic assumptions, build off of them, and then prove what we want. So here is our first line, and we'll call that L sub 1. And I'm going to try to do this without the ruler there. And then we form this nice right triangle. And that represents slope. So if we think about it, like right here, we have our so-called run as one leg of the triangle, and this other leg of the triangle, this right triangle, we have our so-called rise. Okay, so that's just one line, but we have two. So our second line be right here, and that is L sub 2. And we're given that L sub 1 is parallel with L sub 2. And we want to prove that they have the same slope. And here's how we're going to do it. So once again, if we think about the rise versus run situation, consider the smaller right triangle. That goes with the second line. So right here we have our so-called run, and we'll just give that A units. There are A units of run, and here we have our so-called rise, and let's just say that's B units, whatever it happens to be. But likewise, with the larger triangle, that represents L sub 1. So we have this run here and this rise here. And I'm just going to remove that because I don't want this to be too cluttered looking. Now we're given that line 1 and 2 are parallel. But notice with these two parallel lines, we have this so-called transversal. It intersects those two parallel lines. And now we have all sorts of relationships here we know about in Euclidean geometry. So in particular, notice that this angle here and this angle here are alternate interior angles, and those are congruent. But now notice that this angle and this angle must also be congruent because those are vertical angles. So we have the vertical angles, which are also congruent. And then we have this right angle. And a right angle, so to speak, is identical to itself. That's the so-called reflexive principle. A right angle is equal to a right angle. But that right angle is shared by both the large triangle and the small triangle. So right now, we have two common angles. We have the right triangle has a right angle. We have this angle, we have that angle. So this angle here, of course, belongs to the big triangle, this to the small triangle, and this to both. But they're common. It follows by the angle-angle principle that the triangles are similar. But if they are similar, this implies that all sides come in the same ratio. So let's consider this. We have the large triangle. We have the small triangle. So consider that small triangle. We have the rise over the run, so we might say B over A. There's that ratio with the legs of that right triangle, that small right triangle. But the large triangle, because it's similar to the small one, will have sides that are similar. But it's going to be multiplied by some factor because it's bigger, right? So we'll say n times b over n times a. Because they are similar triangles, we can make this move. We have proved that they're similar, so therefore, all the sides come in the same ratio. So here's the large triangle, here's the small triangle. But if we take the large triangle, we can simplify that. So n divided by n is just 1, so that's b over a. And here we have b over a, and that's the same thing. So this implies, therefore, they have the same slope. Pretty cool. But the next proof is more algebraic, so to speak. So let's try it. And this is utilizing, in a way, we might say concepts from linear algebra, when you have systems of equations. So let's say we have y sub 1 equals m sub 1x plus b sub 1, y sub 2 equals m sub 2x plus b sub 2. So that's a 2-by-2 system of linear equations. Now we're given that there is no solution. Why is that? Because they have no common points. They share no common points. They intersect nowhere. So in general, if you have a 2-by-2 system and you're trying to solve it, you're trying to find where do they intersect? Where are the common points, if there are any? But right now, there are none. We're given that. So we want to solve the system such that there is no solution whatsoever. Because they are parallel. They never intersect. And they also have different y-intercepts. So b sub 1 does not equal b sub 2. So let's just solve the system and determine when the system has no solutions whatsoever. So we'll set y sub 1 equal to y sub 2. In other words, m sub 1 x plus b sub 1 is equal to m sub 2 x plus b sub 2. Let's gather up like terms, so to speak. So we'll subtract m sub 2x from both sides of the equation to get m sub 1x minus m sub 2x. And then we'll subtract b sub 1 from both sides of the equation. And so we'll get b sub 2 minus b sub 1. Let's factor out that x from the left-hand side. So x times the quantity, m sub 1 minus m sub 2. And that equals b sub 2 minus b sub 1. We'll divide m sub 1 minus m sub 2 on both sides of the equation. And then we'll end up with x is equal to b sub 2 minus b sub 1, all divided by m sub 1 minus m sub 2. But we know there are no solutions. We also know that if it's right here, if that denominator happens to be 0, if 0, that's undefined. But if undefined, no solutions. I'm just going to abbreviate that. So all we have to do here is just set that to 0. So m sub 1 minus m sub 2 equals 0. So therefore, m sub 1 equals m sub 2. Or in other words, they have the same slope.